The motivation of this paper is to create a method for stimuli selection for eye-tracking experiments, so that researchers can find a subset of stimuli to address a specific need. Eye-tracking technology becomes a widely used tool for autism spectrum disorder in the last few decades. Nowadays, many of these eye-tracking experiments contain over 100 stimuli. For instance, we have 109 stimuli in our experiments from 6 different stimulus groups. The goal of our experiment is to find useful biomarkers to distinguish children with and without autism. Most children can hardly tolerate such a long experiment. If we can select a subset from the 109 stimuli, then we can reduce the length of the eye-tracking experiment and make the experiment more tolerable for young children. We performed data cleaning, fixation identification, and feature extractions for the collected data. Total 9,647 features are extracted from the 109 stimuli. We can use a matrix to represent the whole dataset and split the features into different groups, where each group corresponds to one stimulus. So we need to find the subset of the group matrix that can accurately distinguish children with autism. The easiest solution is to perform a brute force analysis to analyze all the possible subsets, which is an NP-complete problem. If we only have a few stimuli, we can use this method. However, we have 109 stimuli, and this solution is not feasible. Another popular way is to use a two-stage method, where we can train 109 different models in the first stage, and then select the best case stimuli in the second stage. This method is straightforward and easy to understand, but it ignores the interactions among features from different stimuli, so its accuracy might drop. We can also apply recent group selection methods, for instance, group lasso. However, most of these methods are linear in nature, and they could not learn high-level interactions among features. So we created sparsely grouped input variables for neural networks to solve this group selection problem. We also call this method SCIN. The idea of SCIN is simple, which is to apply grouped L1 regularization to the input layer in a neural network. Suppose beta is a family of neural networks, and the beta star, the optimal network we want to find, which is the argument of the original loss plus the regularization term lambda tau. In the formula, lambda is a regularization parameter. A larger lambda gives more penalties for the selected group and will result in less number of groups. Tau is a Frobenius norm of theta I matrix, where theta I represents the weight between group I and the first hidden layer. Visually, we apply the L1 regularization to each group of the input neurons. If group 3 is sparsified, the scheme model will remove all the features in group 3 in the inference time. This means we will not need group 3 anymore in the future experiments. This new loss function is easy to write down, but traditional optimization methods, such as stochastic gradient descent, can hardly converge for this loss function. So we combine stochastic gradient descent, coordinate descent, and the blockwise coordinate descent together to solve this problem. In the training time, we store 2 neural networks in the memory. While performing the blockwise coordinate descent for group 3, we remove group 3 completely from the second network and get loss 2. Then we compare the loss 2 from the second network and loss 1 from the original network. If loss 2 minus loss 1 is within the lambda, we will sparsify group 3. During stochastic optimization, we propagate loss 1 backwards to the network and only optimize the parameters for group 3 and the parameters in other hidden layers. By using this novel optimization method, SCIN can find sparsities and converges much faster. We recruited 64 children for our experiment, where half of them are diagnosed as ASD by clinicians. We applied different machine learning methods to achieve group sparsity. By tuning lambda, the regularization term, we can achieve different levels of group sparsities. In the graph, the x-axis is the number of sparse groups. The y-axis are area on the ROC curve, or accuracy. Group lasso fails to identify sparse groups between 30 to 60 groups, and the lasso performs worse than skin. Skin had the best OC score. By removing 98 stimuli from the 109 stimuli, skin can still achieve 78% accuracy and an 83% OC score. We also performed regression analysis for IQ and the ADOS score. While skin has better performance with fewer sparse groups, it also performs slightly better with more sparse groups. The prediction for ADOS fails completely for all our machine learning methods, and the correlation are extremely low for the ground truth and our prediction. These results might be caused by the small sample size. We only have 30 participants with ADOS score, which is not enough to train a neural network. We also extracted the most important features from our skin model by using Shic value. From this analysis, we find that looking duration on ROIs, quality control, latency, and exploration statistics are all important for ASD classification. Stimuli identified by skin may be reflective and may be good examples of the experimental class. We also examined skin in other settings. Skin can find sparsities in RNA splicing experiments and find unnecessary rows in the MNIST dataset to recognize digits. Skin had the best performance in both experiments. We only have 64 participants for our experiments, and only 30 participants had full ADOS, bin length, and SRS measurements for our regression experiment. Even though this proof of concept study shows promising results from skin, more studies are needed to fully investigate eye-tracking features and meaningful biomarkers for children with ASD. We created a skin model that can sparsify groups, maintain high accuracy, and find useful stimuli for eye-tracking experiments for children with autism. Much work still remains before these techniques, and eye tracking in general can be used in a practical fashion for optimizing treatments and for prediction of longer-term outcomes. Thank you.